So recall that we've been looking at flux integrals. We're measuring a vector field flowing through a surface. Our base case problem is a constant vector field flowing perpendicular to a flat surface. These are two things that we're going to make not constant. So the constant vector field perpendicular to a flat surface. Constant vector field is one thing that we looked at making continuously variable yesterday. We just look at the vector field at a bunch of different places, a bunch of small pieces of our surface. Then we do our calculation, vector field multiplied by some small piece of area, then we add them all up. That's just the integration play that we always use. The other thing that we want to start changing up is perpendicular to a flat surface, which is really both things combined at once. So when we talk about perpendicular to a flat surface, the vector field is perpendicular to the surface and so parallel to vectors normal to the surface. So the vector field is parallel to vectors normal to the surface. So the vector field is parallel to the normal vector. And that's where we're going to start putting in an angle. Huh. So there's a vector field being perpendicular to the surface. So it's going to run parallel to a vector normal to that surface. The vector field is parallel to the normal vector. The angle between those two vectors is equal to 0. So the cosine part of their dot product will be 1. So the dot product will just be the product of the magnitudes. So that means the dot product is just the product of the magnitudes. Which is the multiplication that we're modeling. So V dot N is the magnitude of V times the magnitude of N times the cosine of the angle between V and N. If the angle between the vector field and normal vector is 0, then the cosine of 0 is 1, and the dot product is just the product of the magnitudes, the meters per second multiplied by the square meters. Yes. We would have to know something more about the surface. Let's take a look at an example where we know what the angle is. So what we'd have to do is think about the surface, think about all the locations on the surface, and make a vector from the tangent plane. Remember, the coefficients of the equation of the tangent plane are the components of the vector normal to the plane. So those derivatives are going to give us the direction that we want. You still look like the question. Derivatives, partial derivatives. Remember what we, if we think back to partial derivatives, we spent some time finding the equation of a plane tangent to the surface, right? So if we have a surface and we find our partial derivatives, fx, fy, and fz, those are going to be the components of our normal vector. That's how we built the tangent plane. When we had the tangent plane, fx, fy, and fz at that point was the what we used to build the equation of the tangent plane, but what those numbers represented were the components of a vector normal to the tangent plane, and so normal to the surface at that point. So first derivatives is where we're going to get those. Then the question, of course, becomes how are we going to be describing the surface? And that's when I'm like, all moving on. Quiet, you, because it's messy. Just like it got when we were parameterizing curves. It got messy in that calculation. But conceptually, that's what we're going to do. We're going to get this normal vector with the coefficients of the tangent plane in standard form. All right. So let's look at, once again, go back to our base case and change this perpendicular business. So let's imagine water flowing through a pipe. And because this is math class, we're not going to build a regular, normal person, rationally built pipe. This pipe is a square, mainly because, well, I don't know. What's the area of an ellipse? Ooh, that's the messy version. What's the area of an ellipse if we know the radius? Like the short radius and then the long radius. It's, by the way, the same thing as the area of a circle. I cannot answer because the Fifth Amendment. No Wi-Fi. No Wi-Fi. That's the 28th Amendment. If there is no Wi-Fi, nothing may happen. You know how the area of a circle is pi times r squared? An ellipse doesn't have the same r, right? An ellipse is just like a radius in one way and then a different radius in the other way, and then just kind of like squishing the circle that way. So the area of the ellipse, you know, our major and minor axis is pi times a times b. It's just pi r squared when r squared isn't the same. And we don't get to use an exponent. That's beside the point and not helpful to our case right here, although it will be. It will be. So this is a square pipe because math. Because we do know the area of a square, s squared, and we know the area of a rectangle, length times width. Because a square is the same as a rectangle, right? It's just that the length and the width are the same, so we get to write s squared. We could just as easily say L squared or W squared. Or you could say area is equal to D times H, because I say depth and height. I also always make the length shorter than the width. I always make the length the short one, because people get really mad at me mislabeling things. And I happen to think it's funny. So let's say this is a square pipe with a side length of 4 centimeters. And let's suppose that water is we're going to go back to constant because I'm going to start messing with this perpendicular to flat surface. So we're going to go back to constant vector field, and our vector field is constant. In just kind of running down the pipe, all the same, and we'll put that at I don't even know something I'm not going to be using 5 centimeters per second. If you're a hydraulics engineer and that's too slow or too fast, dude, this is flowing through a fucking square pipe, so don't at me. This is for illustrative purposes only. Now, this vector field, if I put a surface that is perpendicular to the flow of the water, then we can just do our simple calculation. So I'm going to put in a screen here. That's going to be 16 square centimeters. I've got our velocity flowing through at a constant 5 centimeters per second at all these points. And so our flow will be 5 centimeters per second times a 16 square centimeters. $80 cubic centimeters per second. So 5 centimeters per second times 16 square centimeters. 80 cubic centimeters per second. Now what we're going to do is we're going to put another screen in there, and it's going to cover the whole pipe, but it's going to be at an angle. This is why I use this square pipe. So I'm going to put another one. Let's see. Well, of course I did that. It's going to be 3. So I'm going to put a surface in this pipe at an angle. And the angle is going to be 30 degrees with the vertical. So the water is flowing through at 5 centimeters per second, but it's not flowing perpendicular to this flat surface. It's still a flat surface, but it's not flowing perpendicular. Our water is coming through at 5 centimeters per second. But we're not perpendicular. We were perpendicular before to this normal vector. But now our normal vector is coming off at an angle. That normal vector is 30 degrees above my vector field vector. Let's find the area, because the area of this surface is also greater than 16 square centimeters. Because I put it at an angle, I've made one side longer than the other, so it's no longer a square. So the area well, if we pull this out, it's going to be taller than it is wide. So there's 4 centimeters on the floor, but it's taller than it is wide because we've got to figure out the hypotenuse over here. So we've got to calculate the hypotenuse, and conveniently I've used a 30-degree angle. So if this is 4 and this is 2, we can see the hypotenuse is going to be the square root of 20. So the area is greater. Instead of being 4 times 4, it's going to be 4 times the square root of 20. But not all of the 5 centimeters per second is flowing at that angle. I use I looked at it from the side and I figured out the hypotenuse. If this is 4, this side opposite the 30 is 2, because I made a 30-degree angle. So Pythagorean theorem is 4 squared and 2 squared, so 16 and 4. And that's why I picked 30. I didn't pick 30, did I? Because 4 should be the hypotenuse. Was that? No, 3, 4, 5 is a 37. Two is the hypotenuse, not the long side. Dang it. Was that? Oh, this is not a 2 down here. In my mind, I was walking out of my office like, oh, it's not 2, is it? Well, just move the 4. Okay. Sorry, my bad. So we need to figure out the hypotenuse. I'll edit that out. No, I won't. It's important to make mistakes. So we need to figure out the hypotenuse. We've got 4 for an adjacent side. The hypotenuse is unknown. But we have the cosine of 30 degrees is 4 adjacent over the hypotenuse. So the hypotenuse is 4 divided by the cosine of 30. So the area is the hypotenuse multiplied by the width. So it's 4 times 4 divided by cosine of 30. So good question. How did I get square root of 20? I did things wrong. So this is approximately 4.619. So 16 over cosine of 30. Yeah, 18.475. So it's irrational. So more importantly, notice that when I pull this off of 30, I just divided by the cosine of 30. So if I want the area, when I angle this off at 30 degrees, I divide by the cosine of 30, and that tells us what the area is going to be. So notice that we still got the 4 times 4. We've got this 16 centimeters. and it's made bigger when we divide by the angle. So if I move that to a 45-degree angle, I would take the 16, that area of the vertical, on the vertical, and divide by the cosine of 45. If I angled it more, I would divide by the cosine of 60. If you don't like dividing by the cosine, we can multiply by the secant. And at which point you'd be like, well, isn't that the same thing? I'm like, oh yeah, but I have a trig class right after this, so that's where my mind goes. I never would have even brought it up if I didn't have a trig class. Yes. And so that'll give us 18.475. The important part is we take the area and we divide by the cosine of 30. That way, if I make this pipe circular with a diameter of 4 centimeters, we can find the area 5 times the radius squared. And then if I angle that circle off into an ellipse at 30 degrees, we do the same thing, divide by the cosine of 30. But we want how much of this normal vector is going with the vector field, or how much of the vector field and how much of the normal vector is going with the vector field. I need that component. And since the normal is 30 degrees above the vector field, the component of the normal vector in the direction of the vector field is the magnitude of n times the cosine of 30. So the component of n in the direction of the vector field and so the dot product of the vector field and the component of n in the and n is the magnitude of v times the magnitude of n times the cosine of 30. So when we do v dot n, we'll get the magnitude of v times the magnitude of n times the cosine of 30. And the cosine of 30 is going to cancel out the cosine of 30 that showed up when I angled the surface. The magnitude of v is 5. The magnitude of n times the cosine of 30. I'm distracted now because I messed up the circle so bad. The cosine of 30s are going to cancel out. I'll say it better tomorrow. Yikes. So the point is, when we took the area, we divided by the cosine of 30 by putting it at an angle and increasing the area that much. But we want the component of n in the direction of the vector field. That component is n times the cosine of 30. So when I multiply by the vector field with the cosine of 30 in the area, those cosine of 30 cancel out. Still didn't say it right. The cosine of 30s cancel out. I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I'm going to be applying. All right, that's going to do it for today. I'll try to sort my shit out for tomorrow. Everybody have a good day, and thanks for playing. See you tomorrow. Thank you for bringing